wanted to talk about save and load game. I have a horrible slideshow for today. Oh, crud. Hold on. What did I do this last time to get to work right? Do something. Should I go back here? Try this. I'm sorry. I don't know why it's not deterministic in what it wants to do. That's a crap. What do you expect? Like that. I could probably switch to the other slide over. Got to do a little more work. Give me a sec, let me copy this over for everyone off the other computer. Not know why this does this. Wolf's doing it here too. Oh, hey, there we go. Magic. All right. I'm not unplug anything. All right, so I want to talk a little bit about Save Load today. This is a presentation I did last year for the first time, so it's a little rough. And anyway, so I wanted to go through that. One thing, so I was thinking about the, we talked about the sphere collision thing, remember that? that, some of you guys took the Insomniac? How many people took it?
I think I do one.
Everyone? How many people did the math, did the calculations in fixed point math? One of you?
Well, not fixed point, no. I was going to it fixed point.
So I have some stuff, so I was gonna do a sample, because I'm like, wait a minute, the Cindy does fixed point, so everybody convert to float, right? So I wanted to show you something real quick. The ship sailed, but maybe if there's another chance, you'll get to do this. I'll just show you this real quick. So, what they did, they said, okay, we've got, let me bring it up. Probably don't care, this is ship sail, but you never know, it might come in handy some other time. Somebody gave me that in Slack, let me bring it up. Hold on. So I was going to get this done, and I didn't get it done over the weekend because I got to take a dog with that. But, anyway, so they give you the X, Y, and Z. They say, okay, we got X, Y, and Z is in 18 bits and signed 10.8 fixed point. So just some little things I want to point out. So the whole idea behind fixed point numbers, like I said, way back when, I don't know if it was PlayStation 1 or 2, didn't even have floating point math. So we had to do everything fixed point. You want to represent non-whole numbers, but you don't have a floating point unit, so how do you do it? Well, you use what they call fixed point math, where, you know, up there they're signifying, they use 18 bits. And that was, they signify 10.8 like that, or 10, we call it 10.8, but they do that. What they mean is this is the whole part. And this is the fractional part. You probably all know this. But why did they do this? And stop me if you guys already know this. But the whole idea here is we can represent numbers like this. So the way we do that is so if we have a floating point number, like let's say we have a float A, and of course we don't have a floating point processor, but A is, we want to represent the number 1.5. What we can do is we can multiply A, like if we want 8 bits here, that's 8 bits is 256. We can take A times basically 1 shifted by 8, multiplied by that, and that gives us a larger number. In this case, it would be, well, I don't know. Let's do smaller numbers so I can do it. Let's say we're doing 10.4. We'll do 12.4. So we multiply, you know, if we had a number like A is 1.5, and then we want, 4 bits is 16, we shift it up by 1 by our fractional part, and we get a number that's like, what, 16 plus 8, that's 24, right? Am I correct on my math? 1 to 4 is 16, or 1 shifted up by 4 is 16 times 1.5 is 24. So now we got a number that's 24, and then we can convert that to an integer. And now that's a whole number, that's an integer representation of that, but that would be, now in theory, that if we take 24 in hex, what is that? That's 16. Wrong there, my math. Probably 1 shift. Anyway, what we get is we get a number like 1, 1, 0, 0, 0. Yeah, that's right. Okay, that is right, no, that's right. That's, yeah. Anyway, so what we've done now is we've created this number in hex. That is now, if you look at it in 12.4, you put a dot there. Well, if you remember how numbers are decomposed, if you look at how like floating point numbers are decomposed, anything left of the dot is the bit set, we would multiply the bit times 2 to the n, where n is the bit number. And then on the right side of the dot, we divide 1 over 2 to the n, where n is the bit number going that way. So we basically get 2 to the n is 0, 2 to the 0 is 1, and then 1 over 2 to the 2 to the n is 1, or 1 over 2. Oh, my, that's right. Anyway, we get 1 over 2, which is 1.5. Okay, and I screwed up the math, I should have done a shape. But the thing I want to get, so we can represent whole, floating point numbers as pure integers, and then we can that's how the numbers are represented. But the thing I want to get to, is I probably should have put this out on paper, is once we have numbers in integer, what we've basically done is we've created the int version, which is the floating version, times the scaling factor. And our scaling factor is the number of bits in our fractional part. So if we have float A and then we say int A as an int, or A fixed, let's call it, that's just our float. A as a float, let's do this. Times S, where S is our scale. Okay. Well, the whole idea that I was trying to get to is that I think the thing they wanted here that would probably have benefited you is you can do math on fixed point numbers, kind of like you do normal numbers. And the way, and so if we had, well, let's say we had 2 of these, we had A fixed, and we had, if we had A in fixed point, let's say 12.4, and we had a number B in fixed, and we wanted to add those two, and they're stored as, what they call fixed point, compressed fixed point. We can add those two together, so we could say C in fixed equals A fixed plus B fixed. And that will actually add those two numbers. So if we have a number, let's say A in floating point is 1.5, and we use a scale, we multiply by our scaling factor to move it into, basically move it up and then convert it to an int, and we do that with another number B, and let's say B, B float. And I'm just going to use 1.5 also, and we convert B, we convert A float and B float to the fixed versions, and then we want to add them together. Well, if you take A in fixed point, we had 1, 1, 0, 0, 0, because we had 4 bits there, and we had 1.1000, and obviously these are hex numbers. We can add them together, and if we add them together, and I should have done this on paper, I might screw this up, we get 0, 0, 0, 0. We add two of those together, we carry a 1, and we get 1, 2, 3, so we get a 1 there, and we carry a 2, there we go. Yes, because those would add up to 0. That would set that to 0, and then that converts. Yeah, so that adds up right. So yeah, so we add as we add along. We add those two together, those two together, those two together. We add those two together. In binary, 1 and 1 is 0, but we carry a 1. We add 1 and 1, and we had these two together, that would give us 0, because they would carry, we get 1 there, and then we carry again, and that is 1, okay? And so that's what we would get by adding those two numbers together in fixed point. And then if we look at that again and do the math, you know, where I said we take what's on the left side, we take, it's a bit set, we, 2 to the n plus 1, where n is a bit number going this way, and then, we do the same on the right, but we sum basically 2 to the n for all the bits set, and if you look at that, you get, in essence, there 0, and then you've got 1 set there, so that's basically 3, and there your answer is 3.0. So we can add, what I'm basically trying to get at is we take floating point numbers, convert them to fixed point, and we want to do math on them, we can just add them together like normal integers, and the numbers come out. So that again, if we would, the starting numbers are 1.5 and 1.5, we convert them to the fixed point numbers, we just add those together as normal bit numbers, and we get the correct answer. So we could do, and so that may be what they wanted, that may have been faster to just take the fixed point numbers in the sphere info and just add and just do the math there, okay? Now the thing is, you can do that for add and you can do that for subtraction. It works, okay? But the problem is, you can't do it for multiplication. And the reason why this worked here is what we've done is, I did the bit math there, but what I've done is I've added a fixed plus b fixed together, and I got c fixed, and that was the right answer. Okay, but what I've really done is that if you go back to looking at it mathematically, a fixed was a float times the scaling factor, b fixed was b float times the scaling factor. And if you would add those together as mathematical equations, you got a float times the scaling factor plus b float times the scaling factor, and then if we rearrange that, you got what we wanted, which was a float plus b float times the scaling factor, which is exactly what we were looking for, okay? Now the problem is, and I'm running out of board space, but if I wanted to multiply them together to get c fixed, where c fixed was a fixed times b fixed, and I was to say, okay, well, I multiply those together to get c fixed, I just do what Joe said, I just multiply the bit fields together, and I get an answer, but that don't work. And the reason why is, if you look at this representation and you multiply them together, instead of adding, you get a float times b float, or a float times its scaling factor, a float times its scaling factor, times b float times its scaling factor. Okay? And the problem there is, if you look at that rearranged, what that is a float times b float times s, or s squared. Okay? So what we've done is we've shifted that up by another s. So what we have to do then is, if we want to multiply them together, once we multiply them together, then we have to take the multiplied together version and we have to shift it down by our scaling factor, and that gets rid of one of the s's, and we now get the right answer. Okay? Does that make sense? So again, we could multiply them together as if we had a fixed and b fixed and we want to multiply them together, we get c fixed, but because of what we're really doing mathematically, we've blown it up by an extra factor of s. So once we're done, we would have to take that and basically, divide it by s, which would be shifting it down by our one to the fractional bits, okay? And likewise, if we wanted to divide a fixed divided by b fixed to get c fixed, then you'd be doing this, and what would you be doing? I'm going to draw it up here. You would have a float times its scaling factor divided by b float times its scaling factor, and of course the s's go away and you just get a float divided by b float, but that's not what we really want. We want a float times b float times its scaling factor, because we want to keep it in, or assuming it is, we want it still a fixed point version, so we have to introduce that scaling factor back in there. So what we do is, and normally what happens is, because we're representing floating point numbers in fixed point, which is a whole and a fractional part, if we were to divide A fixed by B fixed to get C fixed, what we're doing mathematically, what we end up with, again, is A float divided by B float, and we lose our scaling factor because, you know, it went away. But what happens is, when it goes away really, is we end up with the integerized version of A float times B float, which is, we've got rid of the dot 4, and we've lost all fractional part, okay? And we've truncated our number. So what we do in the case of, if we want to divide A float, if we want to divide A fixed divided by B fixed to get C fixed, is we pre-multiply, and we do A fixed, well, we do, A fixed times our scaling factor again, okay? So we move, so now A fixed becomes we moved it up, so it would be technically become, if we left it in a 16-bit format, we've shifted it up 4 more bits by doing this, so we would end up with, we would lose some of the upper bits, so we would end up with an 8.8, and then we would then divide that by our B fixed, which is B float. Times S, and A fixed, of course, is A float times S. It's a representation of A float times S. Okay. So what we do is we first multiply this up by S, and that gives us A float times S, but we lose 4 bits on the top of that. So if that number used more than 8 bits in the whole part, we can't do that. So what we have to do is, we would have to generally, if we have a 16-bit fixed point representation in code, we would move that into a 32-bit value, which would then give us, you know, we would move this into a 32-bit value, which would give us then technically 28.4. We moved it into a 32-bit integer. Now we moved it from a 12.4 into a 28.4, so we know that because we previously only used 12 bits in the whole part. We know that by moving it into 28, we're not, you know, we've got plenty of headroom there. And then we moved, so we moved into 28.4. Then we shifted up. Then we applied the scaling factor again to shift it up, which then means we shifted up to a 24 dot 8. And then we can divide by B float divided by S, which of course with a 12.4. But anyway, the thing is, once we multiply it by another scaling factor, then when multiplied by the scaling factor, we get A float times the scaling factor times that additional scaling factor. We divide it by B float times the scaling factor, and those cancel out. We get A float times S over B float, and what that really is which is what we want. Okay? Makes sense, and you make probably you're like, we don't care. We're done. We didn't do very well. Anyway, the point I was going to make is you could have done, I think, you know, the thing is you could have done the assignment or the thing completely in fixed point and probably been faster than converting it to float and doing the math. I don't know. You'd have had to test it. The other thing I was thinking of is, and this is what I was going to work on is, you probably, if you really wanted to be fast, you could have parallelized it.
So the question, if I remember correctly, the coordinates were in like, I think,
They were in
different fixed point, and the radius was separate, like 10⁶ or something. And how do you compare, like, can you multiply different fixed point types?
You can multiply different fixed points, and I don't have enough board space to do it here. But if you have, so the radius was in 1.4, and the number was in the numbers were all consistently what, 10.8.
Yeah.
But what you can do, and I don't have enough board space to derive this for you, but if you have A fixed which is in, you know, which is in 12.4, which is, you know, again, A flow. Let's try to write all this out so I can show it to you. Times our scaling factor. And we multiply that by B fixed, which is in 12.4, which is A, you know, B flow, times it, which is a representation of B flow. Times its scaling factor, we end up with, you know, C fixed as a result, which is actually, you know, if we rearrange this on the fly, A flow times B flow times S. So we've shifted it up twice, which we would have here is, technically, if we said, okay, we got enough bits to flow into, we would have 24.8, right? Is what we would have because we doubled the shift. So we moved everything up from 4 to 8, right? Well, I don't have enough board space to prove it to you here, but what we really end up with is A scale plus B scale A scale plus B scale, B scale. These are the fractional parts, and these are the whole parts. So you could actually take for multiplication and division, your result is actually, you know, so if you had a 10.4 here, your result would be a 22.4. So you can multiply them together. You just need to remember that they move into a different scale, and you have to shift them down. Now with division, it's this. So if we divided that by that, we would get, and we didn't shift it up first to get rid of it, we would end up with a 2, 0. And that makes sense because I just told you if we do a division, we lose all our bits. And so you see there 4 minus 4 is 0. And so what we're really doing when we multiply A fixed times that additional scaling factor to do the divide, then we're bumping it up to a 12.8. And then we get the 4 bits, and we maintain our 4 bits. So what we tended to do in the old code, like we would store, I don't remember the exact format was, but we would actually have to check the numbers before we did this step. We would have to make sure that if we didn't have enough bits, you know, if we were still in a, you know, let's say, well, I want 16 bits, we would look at the number and say, you know, what if if it's a normalized vector number, it's usually between 0 and 1, so we're not using a lot of bits up here, so we're like, well, we're fine to move it up. If it was, we're like, oh, well, if we move it, if we shift it up and we're going to blow through, we're going to overflow, then we're just going to have to take the hit and lose it at the end, but then we'd have to eventually shift it back into the proper number. But yeah.
Do you have any kind of documentation where all of this is available readily?
I don't know. The thing is this is like old school stuff that we had to do back in the, you know.
It's really difficult to actually find any 700
A lot of that's why they give you those assignments, is so they're like, well, he can't just go download the answer off the internet, you know.
Yeah. Just the documentation of how to work with fixed point would be nice.
Yeah. I actually have a couple of, ping me on Slack. I have a couple of articles that I've kept around that have a decent explanation. You see this a lot. Well, we saw it back in the day when there just was no floating point units. PlayStation 1, I believe, is where we ran into it. But you see it a lot nowadays in, still in some not really old, but embedded systems. And again, I haven't really looked. I want to look at SIMD docs because I'm like, well, you could probably do this all in SIMD, you know. Of course, I don't know if you could have done your assignment in SIMD because they may have run it on some other processor that did, you know, on an Apple, on a Mac or something that didn't have the SIMD stuff. But yeah, if you remind me, you could have done that. But certainly, even if you did do it in SIMD, you could have done the math in integer, you know, the math for the, because basically all you had to do was take, I think you had 2 points, you had one in the sphere's middle, one in the sphere's middle, and you had a radius, so you had P1 and R1, and then you had P2 and R2, and you just took basically P1 times P2. You want to look at that and see if it's less than R1 times R1 plus R2 or something like that, aren't you? Something like that.
I just squared both sides.
Yeah, so anyway, square on both sides, yeah. But if you look at that, anyway, if you look at that, you're doing you're multiplying each component of that. Well, actually, what you're doing is the dot product squared, aren't you?
I think, yeah, because these are just some coordinates, right? So
Yeah, so P2 dot, yeah. Because you want to find the distance between them, which is the Pythagorean theorem, basically. Anyway, but what I'm saying, so this would be P1 x times P2 x plus P1 y times P2 y plus P3 y times But anyway, what I'm saying here is, you could have done all of this stuff in fixed point, which is basically integer math, which is probably the fastest thing you can do on it, rather than converting it to float. And yeah, you should have been good about it before. I probably could have given you all this. Yeah, I'll find some documentation you can read that probably I should have done this all before I put the screen up by my workspace. And again, most of the time, I guess there were times where we would actually use, use different scalings for numbers and to handle, to control where we wanted our resolution at. Whether we wanted more of it in the, if we had big numbers, we would want more resolution here. If we had fractional numbers like normalized vectors, you want most of it here. So you can store it in different forms, and you can still do the math instead of different forms. You just have to remember to shift it around when you're done. So anyway, all right. So I've got this really bad presentation on save and load. Someone asked about it last year, and so I did a presentation, I did a thing on it, and I thought it was pretty good. Then I looked at the code, and I'm like, oh my God, look at the slides. But we'll go through it anyway. Get the power supply for another issues here. Hopefully, much sleep it is with the monitor. Resolution. Okay, good. All right, so again, this isn't very good. I'm going to try and I might jump around a little bit, just because I think I left some stuff out. So I wanted to talk about save and load. One of the main things to get at, this is really a complicated subject, but I think the biggest thing to get out of here that might help you on if you're interviewing is the buzzword serialization and deserialization. And we probably all know what that is, right? We've all done that. So anyway, I'm just going to blow through these. I don't think we're going to have, how many weeks, what do we got left to end the semester? 2 weeks from today?
Well, last class is next week.
Last?
Next week is
All right. So we only got, okay. I'll just go through this stuff. We don't have time for an assignment on it, but it might give you some bullet points as far as interviewing. I don't know. I don't know how often save and load comes up. But we'll go through it quick. I'll get you out of here. I know you guys got a lot of things you want to work on. So yeah. So the whole idea here behind Save Game is, we ideally, we have some system for creating our world and putting it in its initial state, which for us is Lua scripts, right? Well, if you've done that assignment and you continue to use Lua scripts, obviously Unreal has their own system, UObjects and UAssets and stuff. Anyway, the whole idea here is, we start out and we put the game in a very known state, and then the player plays the game, and it goes in, then the state changes, there's continual state change. But ideally, we would maybe like to save this off, and play it later. Obviously we don't do it Pac-Man, but it's what I had for slide, something I could find on the internet to put on slides. I probably broke some copyright, I don't know. So anyway, so the whole idea here is, we know we can create the game of this, but we would like to be able to save off some information. When it's at this state, we'd like to be able to save some information up so that we can recreate it at a later time. Should you, be in the middle of the game with Pac-Man and need to go do something else. Anyway. Yeah, so, what do we really do? We need to save off the current state of the game such that we can restore the game to that state again. So the big question becomes, well, Joe, what do you mean by the state of the game? And that's what we kind of got to look at. And then, it starts out kind of a simple process, and then maybe gets, we quickly learn that it devolves into, there's some difficulties, and hopefully I'll hit them all. And there's some of the stuff that's not on the slide, so I hope I remember to stop and talk about it. But anyway, just briefly, well, what are we looking at? Well, what we want to look at relevant changes to the state of our game, and I put relevant in here because it turns out that what we find we did when we were working on games at Disney, that we're like, well, yeah, we want to restore the state of an object to the state it was, we look at an object and say, hey, you've changed state, and we want to recreate that state. And we found out, and you're like, well, maybe we don't have to recreate everything about the state of an object. That becomes really, really difficult. And a year ago, I probably would remember what that is, but we just found with certain objects in our game, maybe the position of an object, its orientation in the world was important, but maybe minor details, it wasn't worth trying to recreate, every little thing. For example, we had, in our game, you could pick up and throw crates everywhere, and we found that, it really didn't aid gameplay. What was important was if the character had weaponry on it. Like the character, for example, if the character's running along with a sword, and he's just like this, you're like, well, chances are when we recreate him, we want him in that same position. We want the sword in his hand. Maybe we don't need him exactly in the exact animation state he was in. When we save the game, maybe you do, maybe your game, maybe your game you do, maybe you don't. I don't know. It depends. So, we need to look at, for our stuff. I just quickly put these into categories. Some of the things that are probably important to game objects is, the rotation, orientation of it. But is the exact, and this is again something that may or may not be relevant, but when we propel an object, we apply forces to him, and those forces, you start to accumulate acceleration and velocity on the object, and it, and movement. And it's like, well, do we really? Ideally want to know what his position and his orientation, but is the exact, his exact velocity and acceleration important at that moment. And again, maybe it is, maybe it isn't. And not all games, I don't know, it's been a long time since I played, games like Forza, you probably can't save the game right in the middle of a race, I don't know. Probably too hard. Anyway, so I thought, well, changes to game object, changes to the game object controller, whatever that may be, because each game object controller, it could be uniquely different, So maybe a game object controller, if it's a basic input, handles taking input from the keyboard and applying forces to the object it's controlling, maybe that it has no state of relevance. If you have a game object controller that's a zombie that makes a game object act like a zombie, maybe you're like, okay, my zombie controller, one of his pieces of information is the guy he's chasing after, and then of course I've got a target and I want to move towards that target, and so I control one game object and I'm targeting another game object. So probably if I really maybe my game I want, when it reloads the state, I want it to continue to track that object, so that would be information about the state that I would want to change. Maybe you're like, well, only, maybe I only want to maybe I only want my zombie controller to go back to its state of tracking a certain player if that player is the main character. Maybe he was going after an NPC, and I don't care about, I don't recreate my NPCs exactly, so we don't care about that. And we're not going to deal with all this in Disney. But then obviously you may want to, some of the state maybe, if you have a game where you have a score or number of lives, that's probably information that you would like to recreate accurately. You don't want someone exploiting your game where they get down to 1 life and they know, oh, if I save and reload the number of lives, so I'll just do that. Obviously, that stuff. So anyway, and again, I say, some changes may not be relevant or critical. So, and this is kind of, I wish I'd have updated this with my new stuff, but the thing here is I'm like, okay, well, I try to, what changes in the game object are important. So, like I said, we may determine that his position and orientation are relevant, and we may or may not need to restore the state of its velocity. It's a decision, maybe we're like, oh, I'm lazy. I won't save his velocity. I'll just recreate it and then not worry about it. And then you play the game and the test and complain about, well, it causes a lot of bugs. Anyway, it's non-deterministic. It's something you have to deal with. And and then again we have, I was looking at it here and I'm like, well, we've got a lot of things that touch a game object or look at it, and like I just come up with a case. I'm like, well, maybe my game object controller for a human being or something that controls its health. And so I'm like, well, and that's something I would want to recreate. Again, I don't want users exploiting a system where they know that when their health gets down, they can save and reload, and all the objects' health go back to 100%. Of course, with physics, mass and drag of an object shouldn't change over game time. Maybe they do. I don't know. Maybe I think some people mentioned to me that they're like, hey, Joe, I'm working on a game where my physics objects, I want to change the drag or mass depending on games. But anyway, and one of the things I don't have a good slide on, I realize in here, or maybe it just doesn't flow well, but basically, when we load, when we create our world, we run through a Lua script, and we say, oh, I got a Lua script that creates my main actor. I don't know how you guys did it, but if you looked at my sample, I have a routine that I can hand a script to and say, here's a script, use it to create an actor or game object, and it reads everything it needs to out of that script and creates a game object for me, just to kind of hand it off and it's done, which is great. And so the thing here is, we do that and then things change, and we want to recreate that state. We really don't want to, as you'll see through the slides, I want to introduce this early because it's confusing, is what we really want to do with save and load is we create our objects at start, they change positions, we save off and I'll get to this, we save off the relevant changes, but we don't want to save off everything to completely recreate the object. What we tend to want to do is we save off the delta to the object, and then when we reload the game, maybe I do have that in here. Oh, I do have a slide. Yeah. So what we do is well, I'm missing the first bullet point is we create the initial state of our game, then we want to save the game, and what we want to do here is we want to serialize the relevant changes in game state or in changes to a game object and save it out. Then the thing, the key here is with loading the game, we want to, and we'll get to all this, we want to load the game state file. We want to do things like, well, one of the things, obviously, the state of the game would be what level you're in if there's more than one level. That's something I probably should put on the slide. So we want to determine, what game level they were in, and then we want to reload the game level, which re-puts everybody, which basically does all of the work we did up there at, at initialization. So it goes through the whole thing of reloading the level, and everything pops back up based on where the scripts we created told them to. Then we want to go through and use that state change information that we saved off where we serialize the relevant changes, and we want to apply those changes to all the objects. So basically what tends to happen is, let's say, this chair is relevant to my game, and when I load into the level, the chair is right here at the head of the table, and then for some reason, during the gameplay, the chair moved, and so we re-record. So when we save the game, we're like, oh, okay, this is one of the objects I'm going to save the state. We save off that here, his position is right here, and all we're saving off is the relevant information, which is the change in his position. We don't store up his whole mesh, all his texture and stuff. We just change the relevant information. So what happens is, when we go to load a save game, we say, okay, well, one of the things we stored in the save game is what game level we were in. We reload that game level, which we'll load the chair back to here, and then we go, okay, well, now we're going to apply our save game, which we'll move it back to here. So we kind of, a lot of times you never see it. Everything gets set to its initial position, and then we unroll the save game, and everything moves to where we want it to be and saved. And again, maybe we decided we didn't care about his rotation, so the chair started here, our initial run, someone moved the chair here, and we said, you know what, saving a position of an object is 3 floats. That's not bad. Saving an orientation is an entire matrix. That's a lot of information. So we said, well, in our save game, we're only going to store the relevant position, and so we would reload the world, which the script says, hey, his position is right here. Then we apply the save information. We're like, well, the save information only updated his position, and now he's no longer rotated like he was. But maybe that's not relevant. Maybe just like anything else, save game can take up space, and it can take time to time to process, and there can be issues. So maybe we don't do it anyway. So it sounds all pretty easy if you think about it, or a little easy, but it gets hard. And again, the hard part is we run into a lot of problems here deserializing the save game data and resolving the state set by the loading, moving from our initial state of the game and then applying this information. It turned out to be a little harder than that. So, and I just go through some of the things that get difficult here. The difference between the live game objects at level and the point of the save game. And we run into 2 cases here. What I mean is, again, because we have to do this process, there's no, there's probably more sophisticated save game systems out there, but this is pretty common. But again, we can have this situation where there's a couple of situations because we're resetting everything to its initial state, and then we're trying to change it. Well, what if, like I said, this chair starts out here, but then it blows in our save, it gets during gameplay, it gets blown up and it's gone, and it's not in our game anymore, but then we saved off, we have to record it. Not only, hey, we said we have to record information about the object state, but we may also have to record information about objects that just were gone, And so what would happen is if we reloaded the state of our world, the object's here, and then we want to record something in our deserialization that says, hey, that object really isn't there. And that often could be true. Maybe the initial state of our game was, hey, we had no chair, and in our game is about built-in chairs. So someone built a chair and put it here, and we saved off that information. But then when we reloaded the initial state of the game that we wanted to apply the changes was there was no chair there. So then we would probably have to store information in our save game about putting the chair there. So it gets a little more difficult. And then, we have complex relationships, like I talked about here. We have all of these objects that deal with a particular game object, so we have to restore that, those relationships. Or be able to, obviously, well, the one thing here is, maybe when we serialize game object, well, we can't really, well, we can recreate this and this. We generally do based on the information, but what if the game object controller has changed, stuff like that. So anyway, so I just, you know, couple things, you know, I wanted to, and I don't have, you know, this gets really, kind of like physics, it gets really kind of hairy fast. And so I'm kind of, you know, just kind of giving you guys an explanation of this, again, because some of the students last year were wanting to do save game in their projects. How many of you guys are doing projects that would probably require save game? Anybody? What engine you working in? See, honestly, it probably handles most of it for you, doesn't it? I guess you maybe don't know yet, or? Anyway, so I bring up the concept of serialization events. You know, we have this situation where, hey, you know, my Pac-Man game, this is the 4 game objects in my world, but then at some point Pinky died, and so these are the game objects that I serialize out. So I need to, you know, obviously, if this is the state of the game at save point, I don't serialize any information out about Pinky because Pinky's dead, but I do need to take care of that. And then here's the other idea behind the serialization event. We'll get to it in a minute, but you know, here's our game objects created at load, and then at the save point we have an extra Steve came along. I don't know where Steve came from. He's there. And I have no idea why I put this in here, honest to tell you. I don't know. So anyway, we're going to talk about this, but again, these aren't in the very best order. So again, yeah, I've already kind of gone over this, but you know, here's the kind of thing I was talking about here. You know, we have these complex relationships, and you know, I tried to point out here what we think we might care about keeping track of. Obviously, again, we have to rebuild some of these relationships and that. And so, again, these are in horrible order. But so let's talk. You know, not only do we have to worry about recreating the state, but we have this idea, and I'll probably get to more serialization events where we might have to track object death or object destruction, object creation. And so, you know, how we can do this, and again, it's the idea of serialization and deserialization. You guys all know that. You know, it sounds easy on paper. You know, serialization, literally, I think I grabbed this out of Wikipedia. Serialization is converting a data structure object into a format that can be stored to disk, memory, cloud, etc., and recreated later. And deserialization is recreating or restoring the object to a state at the time of serialization. And one thing, and I try to get to this, and again, these slides suck, but serializing data is pretty easy. We all, you know, because what we're going to do is we're going to say, hey, we need to serialize, we need to write out information about, you know, the change in state of these objects. And if I care about maybe, you know, I decide I care about the position, velocity, and orientation, serializing 2 vectors in a float or 2 vectors in a matrix is pretty easy. You know, we can just write them out with, you know, standard out, C out, or, you know, F right, or whatever. So, you know, so serialization of data is actually pretty easy. The thing that we have to do, though, is we have to serialize it, not only write out the data, we have to serialize it in a way that we can deserialize it properly. And that, you know, that's one thing I was going to put in here. So anyway, so, you know, and I just, you know, I kind of threw some code in here. You know, what if I, you know, this is pseudocode that we don't really do much yet. But, you know, if I cared about, game objects, I could add, you know, functionality, some magic functionality to my game object. You know, I might add I have a serialize function and say, okay, I want to be able to just quickly serialize out what I care about and then deserialize it back in. You know, how do we go about actually implementing these? Again, I don't know why I put this slide right here, but I decided I wanted to talk about where do we serialize to. This doesn't flow very good. We could, you know, where do we serialize to? You know, we might be writing to a file on the system hard drive. We might be writing to the cloud via HTTP. With consoles, all consoles have like a dedicated save area, and they give you an API to write to that save area. And the reason they do that is, there's a couple reasons they do. One of them is they kind of help out with protecting data against hackers. You know, they write it encrypted to a storage area that's not easily to get to as a hard drive. And also they provide, you know, save management. Maybe, you know, you write it up to their dedicated save area through their API, and they may magically transport it to the cloud, to where if you log into your PlayStation account on another computer, you can you have all your saves there, which actually is what, you know, they do now. Because I got a PlayStation 4 Pro, and I was all excited because I hooked it up and installed my games and went in to play The Last of Us, and my save was there. Yeah, technology. Yeah, so and I just point out in here, you know, saving can be a time-consuming process. And so, you know, we generally when we write data, we want to, you know, we may or may not know every avenue or method that's being used to serialize our data, and we may care about the performance of each of those, but we may not know. It may be masked to us. We may not, as a person that's just calling, hey, I want to have this high-level interface where I can serialize data by type and then deserialize it by type when I want to restore it. And I may not know the magic internals, but somebody does. And so, you know, it's generally more efficient for generalized I/O to write data in large blobs, or large chunks of data. And so generally what we do in the back end, and again, I don't know why the slide is here, is we serialize our state data to a single buffer, and then we write that buffer as a blob after serialization is done. We don't write individual components. You know, every time someone says, one of the objects say, hey, I would like to serialize my position, we don't write a 3-float vector via HTTP. You know, we write it to a blob. You know, so this is kind of what we do. We figure out, you know, all these guys serialize themselves to a chunk of memory, and then that serialized data gets written out to the buffer, or written out to memory in one chunk. All right, so, you know, what format do we use what format is our serialized buffer in? You know, we can use XML or JSON. We can use just our own know your own binary format. Most people, usually in general, binary is from a performance standpoint, it's going to be a smaller size, and it's generally going to be faster to create and decode than it is to decode things like XML or JSON. So sometimes I don't understand. How many people have ever worked with JSON? Nobody? I still don't understand why it's so hot. Anyway, I don't know. We won't get into that. Anyway, so my theory is that binary data, creating blobs of binary data and encoding and decoding it ourselves is faster than using formatted files like XML and JSON and stuff. And but the reasons why binary formats aren't awesome is, you know, there can always be bugs and I say time passing. I think the big thing with binary formats are the bugs, and you have to write a lot of custom code to do it. So anyway, I don't know why this. I just put these are probably not tough. But anyway, I started with the idea of, you know, what would a serializer look like if we were going to roll our own, and so we would you know have, I don't know why this is in here, but we would have, you know, some class that is our serializer, and we'd have, you know, some big buffer. We'd have to keep pointing to the root of the buffer because we need to know what to write, and then we keep we keep track of the start and the end of the buffer. Basically, I don't know why it's like I randomized these slides. But we want to create a big chunk of data to serialize to, and then we keep track of the root, we keep track of here, and the end we keep track of there. And then, you know, if you're just going to write data to it, we want to keep track of some write point. And then as we wrote data to it, we know where we're going to write, and we continue to write until we're done writing, and then we say, okay, we use this much of it, and we want to write that. I don't know why this. So, we might have our serializer do all the work, and we, obviously we would want to start writing, it's even more order, but we want to be able to maybe serialize a vector. So, here's my old school version of writing a vector to a buffer. We literally use we check to make sure there's space in the buffer. We mem copy the vector into the buffer, and then we bump our right pointer ahead, whatever size the vector is, and then of course deserialization of the vector would be the opposite. We would pass in a reference to a vector we wanted filled in, and we would copy the data out of there, and then bump our pointer to what the next piece of data is. And this is, again, these are in horrible order. The thing I probably should have talked about that we'll get to is, that writing data to a buffer is easy right there. We just write it and increment where we're going to write to next. And, reading it out is pretty easy, but the problem here is how do we know what, the thing I kind of gloss over is, how do we know what's in the data to deserialize it? As we serialize, we just write it, whatever we want to write, but we probably also have to write some information about what is this data I'm writing. Anyway, I updated my game object serialize, say, okay, if I have a serializer class that does the work for me, to serialize a game object, you pass in the serializer, and then the game object says, hey, write my data out. Obviously, the serializer would have to have if position was a vector 3, and orientation was a 4x4, it would have to, the serializer would have to have functionality for you to write a vector and a vector in matrix 4. We'd have to have, here we've got a vector anyway. So, and here's a really, really bad representation of at a high level. And again, I should have probably talked about the detail, but anyway, here's a very high level detail idea of what my serializer. I want to serialize my game state. I tell my serializer I want to start doing work. I look through all my objects, tell them to serialize themselves to the serialization system, and then the serializer, we end serialization, and then the assumption is something we do something with it after this, and we'll talk about it later. So again, these are all. So the whole idea here is if I did just this, and assuming I had that code there, and I had that game object serialize function and did that, and I had two game objects, player and monster, as I serialize each of them, they would write their position as vector 3, and their matrix is a 3x3 I have here, and then, so that this is what ends up in my data file, is this here, and you can assume this, 12 bytes, which is, a vector 3, and again, this is that buffer I talk about, and it could be bigger than this, but this is what we've written to it. And again, writing the data out is good, but the problem there is, well, okay, we've written data to a buffer that represents a change in state of an object, but how do we use it as value to deserialize it? So that's the problem. I guess I kind of have it in a weird order, but anyway, yeah. So what we want to do is we want to be able to deserialize it. Deserialize that buffer there. And the whole thing here is I loop through all my game objects and I serialize them and write that out. And then again, we want to deserialize it, so we load our level in, which populates our array of game objects, and then we say, okay, we want to deserialize. We want to loop through and deserialize all those objects. But the problem is, well, how do we know? Because this, when we serialize the game, we loaded the game at some point. It played the game for quite a bit of time, and our game objects list, obviously things can die and be created. We may use tricky things like you know, when we want to delete an object out of the array, we might take the object from the bottom and put it in where we're deleting, and then chop the one off the bottom, because that's faster than compressing a vector. So the whole thing here is, you know, the state of our game objects array is undeterministic. So we can't we can loop through and serialize all of them, but we can't assume we can just loop through and deserialize them all, because the master game object list, right after load, you know, obviously like I talked about before, to recreate the game, we're going to load our level, which creates all our game objects, and then we're going to want to deserialize our data file, and we can't assume that these game objects are in the same order that they wrote their data to the serialization file. So we need some way of resolving that up. And so what we end up doing is, you know, we've already talked about, well, you know, we want our game object to have a serialized and deserialized function, so it can serialize and deserialize itself. But what we then we run into this problem, we're like, wait a minute, well, he wrote out the data, but how do I know that because I asked, this is the first guy, and that was the second, how do I know, you know, I need to resolve this information against whatever unique player in my game created that's the same there. And so I kind of said, okay, well, let's roll these two things together, and then let's add a kind of an interface. Let's say, hey, any object that we want to be able to save out, we create a serializable interface, and it's going to have a serialization function and a deserialization function to save its state out and resave its state. And then we're probably going to, I just got to jump to the point that we need to know some unique information about the object, so that we can write that some unique identifier out that says, hey, this was Inky, Binky, you know, Clyde, whatever he was, and here's the serialization data, so that when we reparse, you know, when we start to deserialize that file, we can resolve what that serialized data, what unique object did it come from. And so I introduced the idea of, say, hey, we're going to be serializable. You need to provide me a unique ID that identifies you against anybody else. And so I'm like, okay, so how would we use that? And I said, okay, you know, we want to tell, you know, I introduced this concept of, you know, hey, I'm going to tell the serializer, when I serialize myself, the first thing I'm going to have to do is I'm going to have to, you know, say, I start by saying, hey, I'm a game object, and this is my unique serialization ID to give, so that we can write some information to the file about what, you know, about what's out there, you know, what's going in the file, and then of course, you know, so I say, hey, I'm going to start serialization. Here's the object type I am. Here's my unique serialization ID. Then I'm going to serialize my data, and then I'm going to say, I'm done serializing my object. And you know, we kind of, and you might look at this confusingly, but what ends up happening is when you work on stuff like this a lot, you run into these situations where you're like, oh, you know, I tend to get into these patterns where I need to be able to know when I've started doing these operations and then when they're done, in case I have to do any cleanup. And so we just get used to this, telling the system, you know, I'm going to start, like, just if you look at glib, you know, I have this pattern where say start rendering and rendering, so that it can do start cleanup. I don't know what it does, but I know it's going to do something. The same here. So, you know, we're probably going to have to tell the serializer, I'm going to start serializing an object of this type. Here's its unique ID, and then I'm going to serialize the data, and then I'm going to serialization. And so, you know, or the other way. So that's the way. You know, I did it this way, is if the game object serializing itself, and I'm like, well, what if they forget to call start and? You know, then, you know, the problem here is if we pass in the serializer, the game object, to serialize itself, he needs to make sure he can call start object and start serialization, then he serializes data, and then he calls end. But what if one of these many, many objects that serializes itself forgets to do that? So I'm like, well, let's flip the script, and let's add maybe our serializer has a serialized function for a serializable object. And again, because we've created this base class called iSerializable, that we create an interface that says, hey, you have to have this functionality that I need to do, that I need you to do. I don't care what kind of object you are. I say, okay, you know, I get the class from it. I don't know if I kind of assumed, I'm like, you know, I probably might need to know what kind of object, I might need to know something about the object type. I know I need a unique identifier, and I'll hopefully get to why I do that in a minute. You'll see how I use that. But I'm saying, you know, I probably not only might need to know the unique ID, but I might need to know things like the serialization class in case I have factories to create objects for me, which you'll see I need to do in a minute. So anyway, we flip the script and say, okay, let's not impose it on the user to make sure that they remember to call start serialization and end serialization before they write their data. Let's have maybe we have an interface where every object that needs to be serialized calls mySerialize. I grab the information I need, write it to the file, and then tell the object to serialize itself. And then, you know, I take that work off the user. All right. So I kind of suppose, like, you know, now what we do, I'm like, well, so now we would write out to our file. Before we were writing our vector, our data, it was writing, each game object was writing out its vector, its position, and its orientation. But I decided, well, I'm like, well, that's great for serializing data, but when we do serialize it, it doesn't give us any useful information about what that data, you know, where's the unique object that I can read. I have the changing state for an object, but I need to know which object that was serialized. So I brought in this concept of each serializable object has a type, and I store them as hash strings because that's kind of my go-to way of converting random information to keys, you know, unique IDs. So I decided I'm going to store out the type of the object I'm serializing, and I'm going to store out the unique identifier. And then, you know, because I've done this before, this ain't my first rodeo, I realized, well, what if I just wrote out the type of the data, the type of the object, the ID of the object, and then the information serialized? What if when I restore the serialized data, I can't find that object for some reason to restore a state? So I need to be able to, as I'm parsing through my data, if I can't find this guy to tell him to deserialize himself, I probably need to know how much data is there so I can just skip it. And we have that situation that you might run into that situation, you know, if you're, I don't know, if you're using an older save game with a newer copy of the game or vice versa, you may end up with this stagnant information in your save file. You're like, I don't know what to do with this. But if I know how big the data is, I can skip it. So I just learned this pattern. I was, well, let's store out how much data I have here for this guy in case I just don't know what to do with this, and then I can just jump past it. Because the theory is, for every object we serialize, we query it for its unique, some kind of identifier that says what kind of object it is, in case I need to call a factory to recreate it. Its unique identifier, how much data it's going to write, or how much data it wrote, and then let it write the data. Now, if you're paying attention, which I don't think anybody is, you'll notice, well, how do I write out the data size before it's serialized for itself? And I think I have this in the slide. What we do is we write out, just add this here, let the guy write the data out, and go back and fix up after he's done that. Anyway, this is just an idea, of, you know, based on my, learnings and my rodeos. That, you know, is something that we might use. And the theory is, each of these, I draw them in little boxes, but each of these is a chunk of bytes that was written out by a, whatever my magic write is, which is probably a mem copy. So this would be 4 bytes, and then 4 bytes, and then 2 bytes, and then whatever that is. So these are basically kind of block representations of things stored in a chunk of memory, each of them having a size based on what they are. So I've expanded my, I kind of, again, this is a kind of a different version of what I did back here, just so you can kind of see it. you know, back here, so what I do here is, this is just different permutations, so I get things on the screen. So now, you know, now if I want to serialize all my game objects, you know, I have this, I'm like, you know, I tend to think that, you know, my serializer, I might want to tell them I'm starting to serialize for some reason, I don't know. And then I loop through all my objects, and I say, hey, serialize, I'm going to start object serialization. Here's the type of object, and then here's, you know, its unique identifier, so you can identify it later when you deserialize. And then I tell you how to serialize it, and then I say, hey, serialize over ending, I probably should say ending object serialization. Then when we're all done, fix that. And then again, and this is just to show you, what am I trying to do? I'm sorry. That page. And then I just do this in here. You can look at this later if you want, but I'm like, okay, you know, this is just what starting object serialization might do. You know, again, it just makes sure I have somewhere to write, and I probably should make sure I have the space. But at any rate, it writes out that they pass in their type, and so I write that out. I write it out to where my current buffer pointer is, and then I bump my buffer pointer to that red data there. Then I write out my ID, and then I write out, this is what I was talking about, I write out a dummy size, and I'm going to come back and fill that in later. You can look at this code later if you care about this stuff. And so again, this is why I have a good reason to have end object serialization. I get the names wrong. Because when I start serialization, I want to store out the size of the data, that they've written, so that I can skip it if I have to. But the problem is, that becomes before the data they write, so I end up writing a 0 here, and then they write their data, and then I come back around and fill it in. So in my start serialization, I write out a padding, a dummy data size, and then I skip by it, and then I keep track of, hey, I'm keeping the pointer to where I wrote that dummy size, and then when they're done ending serialization, then I figure out how big the object size is, and then at that point in my buffer, I write that object size, so I fill that data in after they've done it. Again, you can go back and look at these slides if you want. It's a lot I know it's hard to read code and kind of absorb code. So again, we've talked about these information, you know, a couple of problems we ran into with this is, you know, what about extra characters? So, you know, these are the objects that load, and these are the objects at save time. So we got an extra object. So again, what we've done here is now, you know, we started our game initially. It changed to a point where it had an extra character. This is where we serialize. So he serialized himself. But then when we want to load the save game later in time, we recreate the world, and then we want to walk through our save data and reset these guys to what their state was. We've got this extra guy, so we've got to deal with him. And, you know, if we look at what, you know, this is kind of a poor visualization, but this is, you know, what would be written to our buffer, you know, at serialization time. And then at load time, you know, we've got these two objects that we can deserialize with this guy, and so, you know, basically, you know, we need to be able to create a brand new object. The problem we've run into is, you know, we relied on our level creation to create these two objects. And then we just restore the state by deserializing the information in the buffer, in the serialization buffer. But we need to be able to, you know, we need to be able to create a brand new object from what we serialized about that guy. I don't think I kind of do here. So this is the thing that gets really complicated, but I kind of put a slide in here about it. So basically, what we do is, you know, we've got this. One thing we can do is, instead of going through this kind of what I originally had back here. You know, I'm like, oh, deserialization is easy. We just look through, you know, start deserialization, look through and deserialize all our options. Well, we can't really do that. So what we can do though, because we've got all this information in here, is we can iterate through, we can add a system to our serialization to where we can iterate through. And this is where I do a lot of hand waving, but what we can do is, instead of when we want to deserialize our game object, ask our serializer to say, hey, give me the next object ID in the serialized file, and it returns me this unique identifier. Then we ask our world, hey, find that unique object. If it found it, deserialize it based on if we found that we want to deserialize the information in the file. Let me go back. No, I'll use this. But if we found it, if we come to this, here's our next deserialization object. We get it. Do I have one with the ID in there? I think I do. Yeah. So what we want to do here is, instead of just looping through, we want to ask the serializer to say, hey, give me the next. Let's start scanning. Give me the next ID of serialized data in the buffer. Give me the ID so I can deserialize it. If you don't find it, hey world, find me that object. If you don't find the object, we need to create one. We've got this situation here where we've got this new object. So once we get down to here, we say, hey, give me the next one in the buffer, the next unique identifier that only identifies one and only one object. And we ask the world, hey, find that object. If it doesn't find it, then we're like, oh, okay, well, we need to create a new object because it's something that wasn't in the world. And so here's this kind of magic I do. I'm like, well, we have to have some way based on that object ID, we have to have some way of finding a script that will create it. Now we could do that. That's not too hard. I think I have slides in here about that. But basically what we do is we say, hey, iterate through and give me the next ID, ask the world or some master guy that knows about every object in the world, find that object by ID. If it doesn't exist, create one for me based on that object ID, finding whatever script was used to create him. And once you've done that, then we'll deserialize him based on the data in the file. And so basically what it would do here is, we would, during load, our loading would have created our two original characters, and we'd iterate through them. We'd like, okay, find the object by ID world. It would find that guy. We would tell him to deserialize himself, and he would update his position and orientation. We'd say, find me the next ID in our file. It would find this object and return it to me. And we'd say, hey, object, deserialize yourself, which you update the position and orientation. And then when we get to this one, we'd say, oh, find this object by ID. And the system would say, well, these are the only two guys we created at level load. So, and then we would say, okay, well, based on it, we'd have to have some way, based on that unique ID, to create the object. And so we'd want to resolve that ID to a script that creates him. And then the world would create that object, and then we could tell that object to deserialize himself. And I know that's a little bit of hand waving, but it's really not that bad to think about. And then we have this other case where these are the objects we created at load, and these are the objects we serialized, and obviously Pinky died, so we need to handle that. And so we need to delete it basically. So I don't know why. Let me type it here. No, that's. So we need to know. There's a couple of ways. We need to delete this object. And there's a couple of ways, we could do it. But I thought, well, one of the things we used to do is when an object dies, gets destructed, we had some, in our iSerializable class, we had some flags that said, hey, when I die, if I die, do I need to note that for serialization? and that flag was set, then when the game objects were destroyed, if that flag was set to say, hey, we need to serialize destruction, we would tell our serializer serialize object destruction, and we would pass in that ID, and that would it would create a list of all the objects that died during play, and then when it was actually told to serialize the world, it would write out the IDs of all the objects that were dead, and it'd be pretty easy to see what we would do with that. Then, we would recreate the world on load, and then we would have an event that would say, hey, get rid of this guy, and at some point during serialization, probably at the start, before we actually serialize our objects, we would store out all this information about destroying objects, and so we recreate the world here, and then we'd walk through and learn, oh, we got an event that says deserialize a unique object, and then go kill that guy before anybody knew he existed. And I could probably expand on that in here, but yeah. And then I just, I thought, well, and this is just things you can do. I thought, well, we could even, if we want to get really fancy with our Lua script, we could add a section to our Lua script that says, hey, this is the data to create a game object. Maybe I care about, I could create a section that says, hey, I care about serializing this information like position and orientation. And then, in our, obviously, and I don't have code for it, but in our serialization of an object, we would say, what do they want serialized? What do they want stored out? So maybe, maybe an object doesn't care about its orientation or something. We wouldn't add that section. We wouldn't add that section to our Lua code. And maybe if we didn't want, if an object it wasn't necessary for that object to be serialized at all, we don't care about the state of it, then we would just not have a section, and then, obviously the object serialization would check and say, oh, there was no serialization flag set, so he won't get serialized. And you could do, another, cheaper way is just have a flag, basically a Boolean flag that said, oh, this slide should have been first. This is the easy way, and then that was another more complete way. Here we just say yes or no, I want to be serialized. Here we say, by having this section, we say yes, I want to be serialized, and here's the data about myself I want to be serialized. So yeah, so we could do that. And again, it's a little bit, that's not trivial to code, but I don't think it would take any of us that long to figure out how to write most of the stuff. Ideally, I guess I could have more code. I don't know. I think you get the point. I think you start with the basis of serialization and the iSerializable class, and you build on that. But I should have a slide in here. One of the complexities, where is it at? I talked about is handling these complex relationships between things like the player and a player controller. Now, one thing, let me go back here. I know it's way back. But so one thing here is, we may care about, when we serialize the state as a game object, we may have changed the renderer info. We probably may or may not have changed anything about its physics info. And this would be pretty easy to do if we maintained. And I wish I had a cool slide for this. But many students ask me, they're like, well, you can create this system where we create a game object based on our Lua, and hopefully some of you looked at my code. But I create this game object, and then I look through, as I continue on through my Lua file, I say, oh, there's a section in the Lua file that says create physics info. And so it creates one of these guys. And because this guy has already been created, I pass a weak pointer to him, to the physics structure, and he creates, the physics system creates this structure and points back at the object because he needs to know things in order to apply physics to them. And I hope if you look at my, maybe you looked at my code, I don't know. But they're like, well, okay, well, what about, references from him back here? And I talked about it briefly before. I'm like, well, if you need a game object to know about the physics info for him, you can always add a pointer, the pointer from the game object back to here. And it should be a weak pointer because, we don't want kind of the locking mechanism if they have strong pointers to each other because nobody can make each other go away. But anyway, but the other thing is I'm like, well, we may need, when we serialize this guy, we may want to serialize, changes to his mass and drag. We can always ask our physics info system has a weak pointer to the object. We can always, at time of serialization, say, hey, I need to serialize some information out of here. Physics system, find me information about that object if I had to change it. And again, I wish I had a cool slide about that. But the point of what I was trying to get at is, for each game object, if we're centralizing serialization on a game object, we create this, we create that, we create that, we create that, and well, that's our master list. But the object that gets rendered probably doesn't change. The physics info object probably doesn't itself get changed, and we may tweak the mass and drag, and we may have to, when we serialize the game object, we could either tell this guy to serialize himself, or or we could just get the information serialized ourselves. Probably better to tell him to serialize himself. If first we'd have to ask the physics system to find the physics info object for me, and then say, hey, serialize yourself, so that when I deserialize, I create I can tell you to change, deserialize yourself, kind of a hierarchy. But the thing I wanted to get at is, well, what if this guy changes? And so I wrote some pseudocode, because you may have one game object controller on an object at the start of the level, and then you may have a different one at serialization point that you want to reset and find that. Sorry. Yeah, well, this is kind of what I was talking about for both of them. So when we serialize a game object, we kind of create this hierarchy where we see if I can draw it out. I wish I had those two slides side by side. But the whole thing I was trying to get at is we've got a game object, and we've got things that, we've got a controller. So basically, we want to serialize this guy. So what we do is we kind of say, okay, I'm going to serialize my data, but either before or after I do, I serialize information about, if I have a controller connected, I serialize some information about, before we brought up this idea of the iSerializable class, and we based our game object now in theory, and I didn't have a slide that specifically said that, but our game object should be derived from iSerializable, so it creates the interface it needs if that's the way we're going to go, or it may serialize, do it through the serializer itself, its interface. But anyway, so the whole idea here is we can serialize, and our controller should be able to serialize. So we kind of have this thing where, okay, the serializer tells me to serialize, and then I may either serialize my data first, and then ask anybody associated with me to serialize. So we kind of have a hierarchy of serialized data, where, and in this case, I'm like, okay, I'm going to serialize myself. The first thing I'm going to do, if the controller is attached, I'm going to tell him to serialize. So he so what we end up in our buffer of our output, and whatever serialized data we have, the controller serializes himself, whatever he writes, and then I write the game object serializes himself. And so the data gets all written, and we may, I probably should have, had more code here, but the whole idea is, when we get ready to serialize this game object, we write, that header of information we talked about. And then the game object says, okay, controller, we probably write a thing that says, there's going to be, some kind of header that there's controller data coming. And then the controller data. And that's what I'm kind of getting to here. But like, okay, if there's a controller, we're going to serialize it, but we also need to serialize either the unique ID of the controller or some information that there is none. And again, the whole idea here is, before we serialize the game object, we write his unique ID because that's the pattern we're following, and the controller obviously would have to follow that pattern itself too, so that we can deserialize it in the game object controller. And so, now when we deserialize, I kind of switched a little bit of patterns here, but we deserialize to get the unique controller identifier. If there was one found, we say, hey, is that the current controller on me? If it is, tell it to deserialize itself out of our master deserialization data. If not, if it's not the one I want, delete it, delete the current controller, again, create a new controller based on that unique ID, and then tell it to deserialize itself. So it's a similar pattern that we talked about earlier, where we kind of store these unique identifiers so that we can associate, we know what we can query, either for an object out of our master list based on a unique ID, and if he's not there, we create him. The same with the controller. We recreated our game object, which in theory would create our initial controller, and so we store out the type, and then we, here I call it ID, we deserialize to find the kind of controller type that was on us when we were serialized. If it matches what our current controller type is, that's bad pseudocode. If it is, it can deserialize itself directly because it's the right type. If it's not the right type, if there was already one there, delete it, and then create a new one of the right type, and then deserialize it. And if you looked at my code, my sample combined sample, I do something similar to this where I have a factory for creating game object controllers. And if you create your own game object controller, you tell the factory, hey, here's a function to call when you need a controller of a type, and here's the string that identifies the type. And so I have one that does nothing, and I say, hey, game object controller factory, here's a control, here's a lambda. I don't know if I use lambdas or delegates or what, but I say, hey, if you need a do nothing controller, call this function. And so it's very similar to here. What we would do at serialization point is we would write out that that ID. Like if I had the do nothing controller on me, I would, if there's an actual controller on me, I get its ID, and if it was a do nothing controller, that's what I would write out. And then the controller would serialize itself and write his data to the buffer. So what it ended up would be written here is the controller type would be do nothing. And then this would be the whatever do nothing controller serialized. And it would serialize itself. Then at load time, because remember at load, we load the game object back up, we put whatever original controller our original Lua script had on it, but then when we deserialize them, we get the controller type. Here I call it ID, it really should be type. I say, hey, if there's actual type, see if it matches me. If I'm already the right type, just deserialize directly. If I'm the wrong type, or if it doesn't match, delete it, and then create it, call my controller factory to create a controller based on do nothing, and then set it to my current controller and deserialize it. So basically we swap in the new controller and deserialize it out. And in theory, if that all worked, then the controller would be at the right state. So I was going to go through some other stuff that I didn't get in the slides, but you guys look really, really bored, so I think you can A couple things I wanted to mention. If there's anything in here. So I want to talk about, like, obviously if you have actual pointers to other data in your object, you can't serialize the pointers. You got to have the, well, this is kind of what I was talking about here, serializing pointers. So this is basically, what I talk about is we've got a game object and he's got a pointer to a controller on him. How do we handle that in serialization? Well, we tell the controller to serialize itself. Obviously we can't write out raw pointers. That does no value because things always change. But we can tell it to serialize itself and make sure that we write information that allows us to reset them and then deserialize them. So that's what I was talking about there. And I was going to talk about the components of the serialization process, like, do we do the work or does the serializer do the work? We based on iSerializable or do we, or do we not? The big thing is for any data type, here I've done everything as far as orientation and. So the one thing I glossed over is I assumed here my serialization system, and I apologize, I swap back and forth between doing it, most of the work ownership being in the serializer and most of it being in me. But anyway, I talk about, well, I just assume my serializer could serialize a matrix, or a vector 3 in a matrix. But, we may have to, what about other types? And I'm like, well, I guess a couple of things you can do there is have your serializer have the ability to just serialize n bytes of data, and you pass in a pointer and say, hey, serialize, here's a pointer, and serialize 12 bytes of data, write it out, and then I'll know what to do on the other side. I'll know how to, and then have a deserialize that says, hey, give me back the next 14 or 22 bytes or whatever in the file. I should have done slides on that. Well, I talked briefly about deserialization by type, but I don't have code for that. What about other data? What about other things like score and health? Maybe, score and number of lives. Well, we can follow a kind of pattern we've done here where we serialize, we need to, well, draw. Well, I don't really address the problem, the issue of, I just want to write the score out to the data file. So we can, not here we introduce the idea of, back here somewhere. So here I introduce the idea of, it's like, hey, give me the next object ID, and I look it up in the world, and then if I find it in the world, if I don't find it in the world, I create it. If I do, I deserialize it. But the assumption here is our game object. So but what I haven't brought into here because I just can't get all the code on the board is what about things like high score or score and lives and stuff like that. Well, I did briefly introduce the idea in here about being able to store out the type and its unique ID. So what you can expand on this is you can for our score you can say, hey, I need to start serialization for, let's say, number of lives, and then I may or may not need to store a unique ID for the number of lives. I can just set this to 0. But then I can expand. This where I say, hey, serializer, give me the type of the next piece of data in the file, and if the type is high score, then I'm like, oh, then I know that then instead of walking through my object stuff, if the type is the high score, then I can just say, oh, okay, have a special piece of code in here that says, if the next type is high score, then deserialize the high score, which is simply reading an int out of the file and setting my, or the current score, you know, and setting the score. So maybe I'll throw some, I'll throw that code in here before I get here if I can, or before I put these application videos up here, so you guys look for the computer. Got a lot of other stuff we'll talk about. The only other thing is I just want to put out there, you know, we could, because we're serializing into a big buffer and then writing it out, again, it can be time consuming, we found, to write out serialized data. Serializing itself is not that, usually is not very time consuming. It's writing the data out, like I said, if we're writing it over HTTP or something. So what I just really thought about quickly is, you know, we could have multiple serialization buffers, like we could have, you know, 2 buffers to serialize to. And so we serialize our game state to a buffer, and then we pass that buffer off to another thread that maybe compresses that data and encrypts it if we don't want it, you know, if we want to send it over the net, internet, or to the cloud in some way that can't be messed with. And so we have one thread, you know, our main thread, when you say save game, it serializes the save data, and then it starts a job on another thread that compresses it, and then once it's compressed, we can start a job on another thread that maybe sends it over HTTP if that's time consuming. You know, and I just threw that in here. You know, and so here, you know, here's kind of what I was talking about. We serialize the save game, the game state, and then we create a new compression job, and we ask the serializer to give me the save buffer and the size of the save buffer, and then we, you know, we create a new compression job, we create a new write job, and you know, we tell the compression job, you probably look at my code for my job system, hey, compression job, when you get done, start the write job, and then on the write job, maybe send a message on completion that the save game is complete, and then we start the compression job. And obviously, if you look through my code, you know what that would do is, you know, that would start this job, and when that job got done, it would start this job, and when that job got done, that would either send out a message that send out the save game complete message, or the other option we could have here is, if we're using delegates, we could say, hey, write job, fire this delegate on completion, and we have a delegate for the save game is complete. So if you care that the save game is complete, you would be bound to that delegate. And a perfect one way we would use that is if you're ever playing a game. Most games now you'll autosave, and they're like, hey, when I'm autosaving, you see the little spinny thing in the bottom corner, right? So what we would do is we'd serialize the same game. We would put up that little start a job, or say put the spinner up, and then the spinner would listen to the delegate for the save game complete delegate, and when that delegate fired, that thing goes down. And so you don't have to constantly sit there and poll, do I need to take it down, do I need to take it down? You would have a delegate that when that delegate is fired, or you'd have a save game complete delegate. Here I use message with my message type of the hash string, but you would have a delegate and say, hey, fire the save game delegate, and someone that bound himself to the save game delegate says, hey, when it's fired, destroy the sprite for the little twirly thing, or the game object for that. So anyway, this is pretty high level stuff, but I think based on the long code that we have, we do things like that. The other thing I was trying to wrap my head around is if you're using a job system, I talk back here, and this is the last thing I'm saying, I'll let you guys go, is, I run into this situation, I say, hey, serializer, tell me about what's the next object, what's the unique identifier for the next object that's in the serialized data? Say, hey world, give me that object out of your master list so I can tell it to deserialize itself. If you don't find it, I need to create a game object based on that, and then I need to deserialize, and then once you've created it, then I can tell it to deserialize. I'm like, well, you know what? The problem here is, what if this create the object is async, right? And so we don't want to. We'd have to wait here for it to get done. I said, well, you know what you could do? We already have a job system where we have a job. What do I call it? Create actor async. No, I actually looked at my. I don't know. Anyway, in my simple sample I have a create actor async, and I'm like, oh, I could just create a job called deserialize object. And if you look at my code, create actor async, all it is a job system, a job wrapped around create actor, right? It's just really a wrapper with create actor. So I'm like, oh, okay. Well, I could create a deserialized object job. These are both jobs. And I could say, hey, fire off the create this job and tell it when it gets done to call it the deserialized object job. And so I could, if I had to asynchronously create a game object using my, really simple job system, it'd be pretty easy. This deserialized object job is really just a wrapper for the job system around pObject deserialized. And there would be some complications there, like with multi-threaded access to the object and stuff that you could work around pretty easy. One of them would be the deserialized function in an object would maybe lock the object while it was doing it. Or the other thing, actually we wouldn't have to do that, because what we would do is we would create the job to create the async actor, tell it to fire the job to deserialize it, and then when it was done, we would tell it maybe to fire another job to put it in the world actor list. So really what happens is that the actor doesn't get put into our master list or any of our other lists until all of the jobs are completed, or we do a delegate. So. Anyway, just some thoughts on Sapien serialization. I know it's a lot to wrap your head around. I'll try to throw some more code in here if anybody cares before I put the slides up, but I think that's all I had. Yeah. Anyway, that's just kind of a background on how job systems, or how save game kind of works. So, anyway, any questions, comments? Nobody cares anymore. Let's get our projects done for EA day, and that's it, right? Do our finals. All right. Well, we're basically done then. For the last class next Monday, it's the last day of the semester, right? What do we want to do? We run out, we want more material, or we want to, anybody care? Yeah.
Talk about like what's the difference between like developing for consoles and like developing for basically what's the difference between consoles and PCs? Like what are the stuff that we need to look out for?
Well, so the thing is if you're using, now I can't speak for Unity, but if you're using Unreal, we really try to isolate the user from that. You don't have to. I don't think if you write you don't have to write a lot of code for the hardware, right? The way Unreal works is so if you're actually the developer of the engine like us, there's a lot of different things you have to do. But what we do that hopefully makes our product good is we mask that from you. Not only do we we create this workflow based around the editor and working in the editor of blueprints that really, you should be able to, I don't know if you guys probably don't work a lot with consoles, do you? In theory, you can work on, you can write C++ code, you can create your assets, you can create blueprints, and then at the top, in the editor, there's a little button called launch on, and if you got a PS4, you can launch on the PC, but list the PS4 or whatever there. Or on the main menu, there's a thing where you say, hey, I want a package for the PlayStation 4 or the Xbox, whatever, and it just does all the behind-the-scene work to make your project work on the system. Now, the thing you really need to do, and I don't know if I probably have it on here. Let me see if I can find it. I have UE here. And you guys probably don't deal with this a lot, but if you're actually writing a commercial game, let me find, so if you look at the Unreal source, so if you look at the Unreal source, and how many, you guys probably don't do this, but if you've got a project, I don't know if I have a project here, I probably don't, but if you look at the source, we have an engine directory where the engine is, and the big thing that really, that you can, if, the only thing you really would maybe have to do is, and it gets really, this is more if you're like an experienced developer, we have a config directory, and in each directory for config, we have different directories for all the platforms like Android, HTML, iOS, Linux, whatever. You don't see Xbox One here or PS4 because I don't have the code for it. But anyway, inside these directories, oh, and I don't have one, but they have they'll have some unique files, and like, for example, in config, right here we have this file called base device profiles. And what this is, and I don't know if I have any useful information in here, but like, okay, for here, let me see if I can make it bigger. And it really takes a long time to get into this stuff. But here we have, this is the device profiles, and what this does is this helps us configure the engine and how we run based on the device. Like right here, if you're running on iOS, our base iOS, you can see here we're saying our bloom quality is 0, depth of field quality is 0, shadow quality is 2. We have these quality settings that go from like 0 to 4. And so you may go in for any one platform and say, well, I want to set, my shadow quality to 3. I want better shadow on the PS4, or, and we have, like we have, and again, you won't, I can't show you a lot of this stuff here because I don't have the PS4 and Xbox stuff. One, but if you ever do develop for, if you ever get to the point where you're building your game for like the Xbox and the PS4, you have to be a licensed developer with Sony or Microsoft. Once you are, you can, you tell us, and then we go in and set a little bit for wherever you get your, if you're working with, if you're a licensed developer, you're probably working right from our, well, you're either working from our Perforce or through GitHub. But anyway, we give you the magic bits that fills in all of the Xbox and or PS4 files for these, and they've got all this stuff. Like with the Xbox, you can tweak, you can tweak stuff like the anti-aliasing quality and texture quality for like, you can set it differently. Like, oh, if my game's running on the Xbox One X, I'm going to have these super cool settings. And then, that's basically all you have to do. But to make a long answer short, is we really, ideally what we like is if you create your game, in the editor and create your art assets, create your blueprints and your code, we assume the assets you create are probably the highest quality you ever want. You want the best quality. And so when you say package my game, it will go through based on a litany of these settings. We'll say, okay, well, for the Xbox, we might have to compress the textures a little bit more. Or for the PlayStation 4, we might have to, change the default resolution or something. But anyway, basically, we mask a lot of that for you. A lot of developers, once they get really experienced, go, I know for my game on the Xbox One, I want to tweak, or for my game, shadows are really important, so I want to kick the shadow quality up or something on the Xbox One or whatever. So, but ideally, we try to make your game run as best as possible on any platform. So if you're working in Unreal, you don't have to care. If you're working, obviously, if you don't use an engine, there's all kinds of stuff you have to do. Like you have to, if you don't have an engine, you want your game to run on the PS4, but well, I got to figure out how to render graphics on the PS4. But with Unreal, it takes, and I don't have the editor out, but if you're a licensed like PS4, are you guys doing any of that stuff? Are you set up for that?
Not this that maybe.
Because even like Unreal, like when you compile, normally if you're a developer, now you guys just download Unreal from the binaries, we call them, then run it. But most developers will download the source. You can get the source either, like I said, developers that have paid for a support, they can access work right out of our Perforce server like I do. But, or you can get it from GitHub. But if you get it from GitHub, you get the source to the engine, the source to the editor, and they will, if you're a licensed PS4 developer and you install a PS4 SDK to work with it, and then you compile like the editor, we recognize the PS4 SDK is installed, and we enable a bunch of stuff in the editor where you can tweak. You're like, oh, when I run on the PS4, you could, it's a lot like these manual settings, but it's right in the editor in the project setting. You can set different things to tweak your game on the PS4. But like I said, ideally, you may never have to worry about that stuff. You know, there may be stuff you probably have to do. The one big thing I could think of you would have to do for a game on different consoles is there's a way to set up button mapping. You know, to figure out what button does what. The other things you probably have to do is when you build it, when you package any game for like the PS4 or the Xbox or whatever piece of hardware, generally their packaging tools have a bunch of information you have to fill in, like what's the name of my game, what's my product ID I got from Sony, what's, you know, does my game support online features? There's a bunch of information that they require, and so you'll fill in a bunch of information and then package it. And we try to minimize the amount of work you have to do. That's the value in our product. So, yeah. But ideally, if you're not doing a very complex game, your game should run really well on any of the platforms. Like I said, the big thing you would have to do is if you're actually going to package your game for the PlayStation and submit it for manufacturing, there's a bunch of information you can fill in the editor that we then put in the package. That then when you send Sony, like, okay, yeah, I've got your game title, your unique game ID, and you know, they usually require information about what is an online game, to do this, and do that. But a lot of developers never deal with. They can work on their game through 90% of their 90-some% of the product cycle on the PC, and then when they're ready to, you know, do it on the PS4, they just put the package for PS4 or whatever. We spit out a runnable master submittable package. A lot of hard work on the back end though. So that we do, yeah, a lot of. We've done. I mean, you know, I listen to conversations our guys have about the optimizations we do for, you know, things like the Xbox and the PS4 are very, very powerful pieces of hardware, and you don't get that power just, you know, we do a lot of work to make sure that, you know, the GPU is, we keep it as busy as possible, and, you know, we do a lot of work to make sure we're, you know, they have 8 cores, and we make sure that we're spreading our workload out. You know, I talked about here about job system. We make sure we spread our workload out as best we can, use all the cores all the time. So, yeah, stuff like that. You guys, I know you guys are close to being set up for I know you guys do PS4, but you do Xbox stuff. That's good to know.
We're, like, our team is trying to, like,
When we sat down with the guy from PlayStation to talk about like becoming licensed developers.
I don't understand why they make it so hard on students. It's like they're students, they're learning.
One of from our program is purchased from
Yeah, I remember talking to the guy. I remember talking to the guy at Sony about, you know, why they can't. And they're like, well, there's always, you know, well, they're students. They're not like they're, you know, I can understand the process for professional developers and games that are producing, or companies that are producing product. Give them a pass, but they're kind of funny about it. So hopefully you get to do it. That'd be cool. Yeah, there was one that was. I remember it was 2 years ago. Yeah.
I mean, it was there on the Facebook.
Anyway, yeah. So if you got more questions, any other questions? All right. Well, we're done then. I'm going to think about next Monday, because if nobody has anything really good that they want to learn, then I don't know. It's the last day of the semester. Maybe we'll just bag it and work on it final. that's a good idea. But I'm gonna come up with something I figured I'd try thinking what I missed out on. All right, we're done.